So we're going to see it again and again and again. All right. So we'll start the next chapter. I'm going to just get it set up. We can find it. So this here, we're looking at multiple regression. Now I'm just looking at adding just one more predictor, right? So if you think of the age of the car, you could add a predictor. Another possible predictor, right? So we would give it beta 2 and x subscript 2. And then that's the model that we estimate it using the hat. So the true model, the true values is y equals beta, all those betas, beta naught plus beta 1, x1 plus beta 2, x2 plus the epsilon, which is the error, right? That's the error terms. Then we estimate that model, that true model, using the b's, the y hats and the b's, just like we did. And we have now another. So we don't have a best line. We have, does anyone know what we have instead of a line? If you have two x's and a y, it's not just a line. It's not just two dimensions, right? It's not just x and y anymore. It's going to be x, x1 and x2 and y. So instead of a line, what do we have? Yeah, a plane, exactly. A plane. And you could see if we added another one, x3, we would be into 4 dimensions, which some people say they can see, but I can't. And then 5 dimensions, it starts, you can't see it. You just have to use the mathematics and analyze it from there. Yeah, so it is a plane. Think of it as best plane of best fit, right? So here we do inference about the regression coefficients. So we can do for B1, we could also do, and I didn't add this in, but I can now. You could also do for the second one. So we have the slope coefficient. We have 2 slopes. When you have a plane, you have 2 slopes. So you have beta B1 and B2. So you would just test it and you could do this. And I think for this is just alpha over 2 times S of B2. I think on the formula sheet, it just says subscript I, where I can be 1, 2, 3, 4, 5. Okay. Let me just go to the formula sheet and make sure it does say that. No, it just says 1. But here is where it would be. Right there, it says 1, but you could use 2, you could use 3, you could use 4. It could be any slope. Okay, so even though it says subscript 1 right here and here, you could use it for 2, 3, 4. Okay, and if there's, yeah, so here's showing 2 slopes, B1 and B2. You could have B3, and that would just extend this even more to more predictors. Okay, and you can test the same way. It's always the same, equal to 0 or not equal to 0. That's what we want to know, right? And there's 2 ways to test. You can do the t-test. You can do the t-test, or for the individual slopes, you can use the t-test. For the overall model, you need the f-test, the ANOVA. But for each individual slope coefficients, you can use the t-test for each one. Okay, and then you can go, is this coefficient in or is it out? Right? If the car has extras, like, what do you call it? Low, when it's loaded, when it has like if it has a new stereo or something that could increase the price, or a new tracking system, you could have that in there or not. And it may be significant, it might not be, and you would test to see. All right. And then evaluating the whole model, this is the ANOVA. This would be the overall ANOVA. So this would be the ANOVA right here. That's when you're testing if all of the coefficients equal 0 globally all at once. And the alternative is at least one of them is not equal to 0. Okay. And if you want to test them individually, you just do the t-test. Okay. And it goes up to k, subscript k, where k is the number of predictors. Just like we talked about with the ANOVA table, k is the number of predictors in your model. Okay, everyone's with me? Good. And here it is here. We have our overall model. It's the ANOVA table. This tests the overall model to see how good. F can be a function of MSR divided by MSE. It can also be written this way. That's how we get those MSRs and MSEs, those mean squares. Or you can also get it if you know R squared, you can also get the F value using this formula. Whatever you have handy, that's what you use. Most of the time it's MSR divided by MSE. That's the most straightforward. That's because we usually have the table. And there's the sum of the squares for the regression. Remember, that's the line. In this case, if there's two predictors, it would be the plane. So how the y hat varies across the plane, right? How it changes. The residuals is how good the data points are to the plane. And then the sum of, we have an O there, the sum of the squares of the total. Right. Best way to do this is to get through an example. By the way, sometimes the book will show it n minus k minus 2, but if you look at this, n minus k minus 1, that is the same. So if you see it as n minus with a bracket k plus 1, it's exactly the same as n minus k minus 1 when you remove the bracket. Right? If you remove the bracket, it would turn into n minus k minus 1. Just some little algebra there. It's exactly the same. And that's our standard error for the model. They call it the standard error of the estimate or the standard error of the model. It's all the same thing, and it's interpreted the same way. 68% of the errors will be plus or minus 1 times the standard error, the little SE. Plus or minus 2 would be 95% of the errors. And it's a way, we want to know this value because it's a way of checking the fit of the model. How good is the model? Okay. And then we also look at the R squared. It's a little bit indifferent. The interpretation is different than the simple linear regression because it has, it's analogous to R squared in the simple regression, but it requires a different interpretation and a different computation. So it represents the proportion of the total variation in the dependent variable about its mean as a predictor collectively. So it's taking into consideration the variability about, if it's a plane, let's say, it would be across the plane. Okay. And you can see it's the textbook has an O with that, but just know SST is the same as SSTO total. Some textbooks just have SST for total. So it's the sum of the, just think it's the proportion. That's a proportion. So you take the sum of the squares of the regression, that's the variability amount around the model, divide by the total variance. So the regression variance divided by the total variance. It's the regression variance is the regression that we know. Divided by the total. It does not tell you, though, which and how a given independent variable is contributing to explaining the total variation and why. It considers them all together. Okay. All right. And then what we do is we also have what's called adjusted, because if I add a predictor and add another predictor and have, let's say the more predictors I have, this is going to become really good. And you're going to artificially have a fantastic model. For example, 10 predictors would be better. It'll have an R squared closer to 100% than say 5 predictors. A model with 5 predictors. So it's an artificial way of, it'll just because of the formula, it will artificially go closer to 100%. So we use instead adjusted R squared. We look at it, and this will penalize or take into consideration the number of predictors. So you can see it's 1 subtract the sum of the squares of the error divided by the degrees of freedom, the n minus k minus 1. And then you divide by the sum of the squares of the total divided by n minus 1. This is also 1 minus the MSE divided by the SSTO, there should be a little O there, divided by n minus 1. Can be done that way too. It's on the formula sheet for you to check, just like that. There it is there. Okay. And it takes into consideration, so it's going to be not artificially increase with every predictor that you add, because you don't want to go, hey, I have this wonderful, great model. Look at my R squared, it's 95%. But if you have a lot of predictors, it's kind of been made to be that good. Where here, this will kind of take into consideration both the additional information each new variable brings to the regression model and the change degrees of freedom in the denominator. Notice K is in there. So K is taken into consideration. K, what is K? K is the number of predictors. So it takes it into consideration. And the total. And it takes, it's 1 subtract that. So instead of having, instead of having the SSR divided by the total, it's going to be 1 subtract the MSE divided by the total divided by the n minus 1. So yeah, so sometimes additional independent variables add no significant information to the regression model, but the R squared will look fantastic. So we used adjusted R squared. So the gap, there's usually a gap between the adjusted R squared and R. It will increase as non-significant independent variables are added to the regression model. You'll see how the R squared will keep going up, but the adjusted will stay. So the difference also increases as n increases. The more data you have, it will also increase. That difference will also increase. All right, because it takes into consideration the size of your data. And so here, notice this example. Do you remember the online sales example we used in chapter 14? We had that online chat feature and we wanted to see, should the company keep it? Because it's using its AI. Sometimes the chat features have AI. They are real people sometimes, depending on the time of day and so forth. So we had time spent in minutes, right, was our X. And then we had the online sales. But what if we had the age of the customer as well? So then we could have two values. And I have this ... This means that we have 26. I've added more customers just to keep it interesting. So this would be our Y, right? Sales, same Y as last time. And we can call this one X. Well, this was our first X, wasn't it? It was our first one. And then this one can be X2. Seems a little backwards. I could have done the chart with Y, X1, X2, but yeah, so I've added age, the age of the customer. And then we can just run a multiple linear regression. But here's what it looks like. You can see age, the relationship between age and sales, time spent and sales, and then age and time spent. So the plots don't tell us too much. This is exactly what my research was about with creating GenSet and R package and that, right? You can't tell from the plots. So what can we do? The plots don't tell us what's happening. Not really, right? We can't really see any relationships, anything happening. So what we do is we run a regression. In this case, a multiple linear regression. So we have reached a point in the course where we can't calculate the coefficients. we need Excel to calculate the coefficients. So from this point on, you will be given a table of what the coefficients are and or the ANOVA table, because we can't actually come up with, remember how we had those formulas for the simple linear regression? We could come up with the slope and we could come up with the intercept. When it becomes this more advanced, this is way more predictive analytic, we're getting into more advanced modeling, we need Excel. So this is the output from Excel. We have coefficients for the intercept. It's just negative 6.933. And it corresponds to the standard error. So the standard error is literally the entire denominator of the intercept. Same with time spent and age. So time spent we called x1. I'm glad I called it x1 on the previous slide. So we're consistent. And age is x2. So what is the estimate for the time spent coefficient? So just to let you know, the standard errors, so it's giving you the coefficients and the standard errors. The output gives us, see all these purple standard errors I highlighted last time? It's actually giving those values. So it's giving, this is what the output is in the multiple linear regression. It's giving the standard error. So all you need is just that number and go get your t, and you can come up with what the t value, what the test statistic is. If you do this here, you know the coefficient because it comes out on the Excel, and you know the standard error comes out on the Excel output. So that S subscript B1 is the standard error. Okay. This is the standard error, SE, and this is the standard error. Okay. Yeah. So can't really do these by calculator. Definitely need the Excel add-in, data analytics add-in. So what is the estimate for time spent? So it's going to be B1 because it's X1, and it's going to be 0.906. That's the estimate. You just literally need to learn. The part of this chapter is learning how to read the output from the Excel. And then after the midterm, we're going to be using the Excel to get the output ourselves. Okay. So we have B1. So the age coefficient, what is the estimate for the age coefficient? It's B2 because it's X2. X2, B1 goes with X1, B2 goes with X2, and it's going to be 1.217. And then it's saying, what is the multiple regression equation? It's going to be, you can do this actually. You can go sales with a hat, because that's our Y. You can write it either way, equals beta naught plus 0.906. Actually, we have beta naught, don't we? We have negative 6.933. Let's put it in. We know what it is. Negative 6.933, because it's this. Y hat equals beta naught plus B1 X1 plus B2 X2. That's our line. So I'm just going to plug those in. That will be a plus. And we're going to multiply by time spent. And this would be plus 0.906. And time spent is simply X1. And then you can add 1.217 times age. Or you can go 1.217 times X2. So in words is nice. I'm actually working on a research project for emergency medicine, and I'm thinking I'm going to give it to the doctors in words because they won't know the notation. Sometimes that is handy in a report. You can give it to, you can say, well, sales is equal to negative 6.933 plus 0.906 times time spent plus 1.217 times age. Okay. Yeah, because if I'm working with a lot of emergency medical doctors and they don't want to see any math or code or anything. And they don't even really want to see this much. But if you give it in words, and do you find it helpful too? Right? It's sales. How do I get sales? Well, I'm going to get sales by having a coefficient, an intercept, negative 6.933, and I'm going to add 0.906 times the time spent in minutes and add 1.217 times someone's age. Done. And if you're comfortable with notation, that's okay too. You can do it that way. Either way, it's good to know both because the course will possibly have just notation too. So know the notation. So then it says same output here. The next question is, what is the value of the test statistic for the time spent coefficient? So the value of the test for time spent, so that's going to be T, we'll call it T1 because it's going with B1. It's going to be B1 over S1, right? And so it's literally just 0.906 divided by 0.317. That's the standard error. So this is, if you wanted to see it, this is B naught, B1, B2, and this is S naught, S1, S2. That's what the outputs are. And you want to get used to seeing them like that. The coefficients are the B's from the equation, and the standard error are the standard errors. And so we just plug that in, and we got the T. Does anybody have a value for the T? Just need to find the value for the T. Yes. That's what I get. Perfect. Anybody get anything different? 2.858. Good. And then we want to know, in this case, and you might be going, well, we already know time spent is significant. Why do we need to do it again? It turns out, and this is really common in business, when you're looking at regression relationships in business and econ, sometimes by adding a predictor such as age, it may reverse the significance of the variable you already tested by itself. So we still have to check and make sure it's still significant. If it's not, then we throw it out. We don't use it. So when you introduce, this is how these relationships all work together. They may work together, or the age might bump it out. Okay. So you never know what you're going to get. So we find our T critical, right? We're going to get a critical value. What is our degrees of freedom for this model? It's not n-2 anymore. What should we use? Degrees of freedom for the multiple regression model. Yes. Perfect. Yes. N minus K minus 1, which is N in this case was 26 customers, minus what's K? 2 minus 1 is going to be 23, right? 23 sound correct? Now we can do a critical on 23 degrees of freedom. I need to check and make sure our table goes like that. Let's take a look. Does it have a 23? It does, right there. Nice. So we have a 23 degrees, and we will get that value there because we're using alpha. It's a two-sided test. They're 99% of the time it's a two-sided test. So it's a two-sided test, and we'll use 2.069. Okay, compare the two values. Are we going to keep the time spent, or are we going, is it good? Compare that value to this value. If it's good, we keep it and it's a good predictor. If it's not, what are we going to do? What are we hoping for here? Yes?
The observed p-value is greater than the critical.
And it is, yeah. So t-test is greater than the t-crit, right? 2.858 is greater than 2.069. Is this what we're hoping for in this case, right? Yeah. So that's good. So therefore we reject. We reject, and this is good. This means that time spent is it is a predictor. It is significantly associated with sales. And you would just say that in plain language to the CEO or whoever, the manager, whoever you're reporting to. Okay. Based on your answer for part A, B, should we keep the time spent variable in the model? Yes. We want to keep it, because if you reject the null hypothesis, just remember we're rejecting, this is what we rejected. We rejected that B1 equals 0, and we're accepting. So this is what we're rejecting. We're saying no, it's not equal to 0, and we're accepting that it's not equal to 0. So that's good. Okay. Even though it's 0.9, think of the number, 0.906. I would almost want to do a confidence interval on it too and see how close the confidence interval, the lower bound, gets to 0, because sometimes that can tell us too. You know, what's the effect size, we call it. How much of an effect does this have on sales? What is the value of the test statistic for the age? Now we need to do for the age, so we'll call it T2, and we're going to have B2 over S2 because it's the second predictor. And you literally just plug those in, 1.217. Just remember this was B naught, this was B1, this was B2, this was S naught, S1, S2, and it's just literally plug those in. And we're going to do exactly the same thing. And we get, does anyone have a value for the test statistic? A value? Anybody? 3.71. Sure, 3.71. Yes. And then we do the same thing. Is it statistically significant? And you don't have to double your work. You can use exactly the degrees of freedom stay the same. It's going to be the same critical value that we just did. It's the same degrees of freedom because it's the same model. Okay. And we compare those two, right? And we're going to remember we're looking at this B2 equals 0 versus the alternative B2 does not equal 0. We're hoping to reject that it equals 0. So is it? Yes. So since the t-test, which is 3.71, is greater than the t-crit, we reject H naught. So this is out and this is good. And should we keep age in the model too? Yes, we keep them both. So we have a two predictor model. And now we can proceed at this point to go ahead and make predictions. Now, if you go back to the pictures I had here, you'll see that this would never have told us that, right? These plots would never have said that there's relationships among those variables at all with 26 customers. Imagine having 100,000 customers, like just becomes too much, right? So you would, right, just think of Amazon on Black Friday, how many customers? Definitely need more than that. That's when you go beyond the Excel sheet, then you need Python, right? Okay, so we have good predictions here. What is the 95% confidence interval for time spent? So instead of the t-test, we can get the confidence interval. And this is good. I'm glad I put this on here because I want to see how close to zero it is. And that's the formula. That's it. We already have everything. And so we just go 0.906 plus or minus RT. RT is 23 degrees of freedom. Everything stays. And I believe it was 2.069. Yep, 2.069. And then we're going to multiply that by 0.317, right? The standard error for one is 0.317, and we get a lower and upper bound. So let's see what we got here. How close to zero does this get? 0.250 to 1.562. Does anybody get anything different? And it's not too close. And had it been, if the lower bound had been 0.009 or something like that, that was really close to zero, then I would have been a little more nervous and go, you know, it's close to zero, but we're not. We're 0.25 to 1.5062. Since zero is not in the interval, we have statistical significance. Okay? It means time spent is significantly associated with sales. So this is where we really use t-tests and confidence intervals. You probably learned how to do those confidence intervals and hypothesis tests in econometrics, but here is where we really need them, those tools, because they tell us whether we can use those in a prediction model for the company, right? Really, really applied. What about the next one? We need a confidence interval for the age. Same thing. We're just going to call it B2 because it's 2. And you just get your T and you multiply it by S2. And you just literally plug that in. These are just 1.217 plus or minus. It's going to be the same, 2.069 times 0.328. And then we can see the magnitude of the lower value. So the lower value I get is 0.538. So it's good. It's not like it's really, really small. It's not 0.00001. It's still far from zero. So it's 0.538 to 1.896. And again, you can come to the same conclusion since zero is not within the interval, within the range, or whatever way you want to say it. If it's not within the range, we can conclude age is significantly related to sales. Plain language for a manager who knows very little about data analytics. Right. And what does it look like? Well, we can test the overall model too, as well. We want to see, we know that the individual, the individual predictors are good. Now we need to look at how is the overall model. Okay, so what is the multiple? So we have these series of questions based on the ANOVA table. And what is the multiple coefficient of determination R squared? We can get that. What is the adjusted R squared? We can get that. The standard error of the model, the value of the F-test statistic, the critical value, and finally, what is the conclusion for the overall model? We can do all that right here. Quite often, these questions will come to you as being partial ANOVA tests. So you might only be given a couple of entries on the table, but you will be given a narrative knowing the size of the data, how many predictors. You need to know the size of the data and the number of predictors to fill in the degrees of freedom. For example, here we know n is equal to 26, and the total variation, SSTO, it has degrees of freedom 25 because it's n minus 1, right? N minus 1 is here. This is n minus k minus 1, and this is k, right? K is 2, right? N minus k minus 1 we said was 23, and n minus 1 is 25. So you know how those fit on the table. And we have our variations for the sums of squares, our variation for the residuals, and the MS, the mean squares, and the F. So let's just fill it out. We can just I'll do it like this. A is, what is the multiple coefficient? So R squared is literally, it's just the formula sheet tells us it's SSR, the variance, right? The source of variance about the plane. In this case, it's a plane, not a line, divided by the SSTO total. And we have that. SSR is going to be 9618. No, 7759, right? 9618 would be the SSE. So 7759 is the numerator. You want to try to keep these straight. 7759.146 divided by the SSTO is 17377.846. And we have it. Once you have that, you have your R squared. Does anybody have an R squared? Yes. Perfect, yes, 446, and we can put that as a percent, 44.6, so it's not bad. It's actually pretty good, not bad. And then the adjusted R squared, we want it to because it will take into consideration that there's 2 predictors equals 1 subtract the SSE divided by n minus k minus 1, which is the MSE, and then the SSTO divided by n minus 1. So 1 subtract. The SSE divided by n minus k minus 1 should just be 418,204, right? Or I can fill it in. 9618.7 divided by 23. That should be the same as 418.204. It should be the same thing, right? So then we have the denominator too. It's going to be 17,377. That's the total, 0.846. Divide by 25. That's going to be 1 well, we'll just put it all into the calculator and we should get 0.398 or 39.8%. Can you verify? It's always good to verify. And you have 39, 38? I think we'll take a quick break, but before we do, we'll come back and we'll pick up on this and finish the chapter, because we want to get into what if we have categorical we can add a categorical predictor. We'll see how we can do that. But this is what it looks like. There's our points, our 26 customers. And we have age along the horizontal. The height, we have sales. That would be our Z, our height. In our case, it's Y hat. And then we also have time spent, right, along the width times height, right? Length, width, height. And then here is what the model looks like. It's the plane, right? So that plane is equal to whatever we had. Y hat equals B naught plus B1 X1 plus B2 X2. And we have the coefficients and we know it's time, X1 is time spent, and we know that age is X2. Right? X1 is time spent, X2 is age. Right, so we'll take a 10-minute break. How about we come back at 1:50? We'll 1:50? No, 12:50, right? Yeah, 12:50. I got to get back in the swing of things. Okay, we'll come back in a few minutes, okay? Have a quick break. All right, so part C. So we have, actually, we could compare these two, R squared and adjusted R squared. R squared almost always will be higher. Sometimes they'll be close, but 44.6 versus 39.8%. So the adjusted R squared is usually the safer bet to use and to report. You can always report both as well. Okay, part C, we want to know the standard error of the model. And we know that that is the square root of the SSE divided by n minus k minus 1, which in this case is 23. But the SSE, it comes to us from the table. Can anyone tell me what the sum of the squares of the errors are? E stands for errors, right? So, right there, 96. Everyone agree? 96, 18.7. 96, 18.7. And we're going to divide by n minus k minus 1. 26 minus 2 minus 1 is 23. 23 degrees of freedom. And that will give us our SE, which is 20.450. Good? You agree? So pretty much I know we have a quiz next week, but you can also start working on the practice questions from the two practice tests. So then you have lots of time and it will give you, you'll be more relaxed if the sooner you start those, because then once you've gone through them, you will feel like you understand the material, and also review the quizzes, right? They're good to have too. So part D is the F test. And it is going to be, I'm going to use this MSR divided by MSE because we have both of those, because we have the ANOVA table. The MSR is going to be 3879.375. And the MSE, which is the mean square error, it always goes in the denominator, 418.204. So let's grab those. 3879.573. Divide by 418.204. Right. 9.277. And you'll really like when you do start working with the Excel sheet because it gives you the t values, it gives you the critical values, it gives you the p values, it gives you the confidence intervals. It's just all done in one click of a button. But you want to understand them. That's why we're working through them, because you want to understand what those outputs mean, right? So, and I get 9.277 for the F test. And we're going to compare it to the critical value. Now, the F critical value, what will be the degrees of freedom? I'm going to use the alpha 0.05, but what would be the degrees of freedom? I should look, I need two, right? DF, there's going to be a DF1 and a DF2. What's the degrees of freedom? 1? And look at the table. The table will tell us. Degrees of freedom 1 will be 2. It's actually 2, right? It'll be 2. It's the number of predictors. And the degrees of freedom 2 will be, so 2, the degrees of freedom for the denominator will be n minus k minus 1, which is 23. So you always, for the F test statistic, the F value here, you want to get you always want to use 2, 23. So the degrees of freedom for the regression and the degrees of freedom for the error. In that order too, 2 and 23. So let's get the F table. See if we can find those. So we want 2. So the numerator is going to be, this is our numerator, will be a 2, right? 2 predictors. And our denominator will be n minus k minus 1, which is 23, which is going to be right here. And we find the cross tabulation. Can everyone see that? 3, let me just see. 3.42. Right, 3.42. And we're always using the sheet. You may find, I have posted all of the sheets if alpha is 0.01, because I think some of the questions in the practice test go into other alphas, which is okay. But know that you'll be given this 0.05 for our test. So that's 3.42. And we want to compare that. So we want to compare this value here with this value here. And how do they compare? Do we have a good model overall? Right? Remember, the null hypothesis is all the coefficients equal 0. All of the coefficients versus at least 1. The alternative is at least 1 does not equal 0, but how would we conclude here? This is F. Part F. What do we do? So the F test, since the F test, is it greater than the critical? Right? Yes. Greater than the F critical. This is good. Then we reject the null hypothesis, which was B naught equals B1 equals B2 equals 0. We're going to reject that, and we're going to accept the alternative that B naught does not equal equals B1 equals B2 does not equal 0. and this is good. So this is a good fit. This is a way to assess the fit of the model. So we have a good fit over, this was an overall, the ANOVA is the overall test, right? And I'm just going to go back to let me find the beginning of these slides. We talked about the overall. Yeah. So yeah, the alternative really should be written in words. That's why I was looking at it a little strange. So the null hypothesis, which we rejected, is all of the betas are equal to 0 and each other, versus at least the alternative is just in words. At least one of the regression coefficients is not equal to 0. So let me just, to keep this clean, this would be at least one is not equal to 0, right? At least one of the coefficients is not equal. So this is good. And because we did the F tests and the confidence intervals, we know that both time spent and age are significantly related to sales. And we now know with R squared is okay, adjusted R squared is good. Those are actually good percentages with real data, considered okay. And we know that the overall test is good. So we have a good model. And here are the 26 points I showed you earlier, and there is the plane. Okay. We move on, some caveats. So influential observations, just some terminology here. Influential observations are outliers, and they are typical data points that influence, for the worse, the nature of the regression equation. Okay, so there's outliers that don't influence the outcome, but then there's some that do. By having them in the model, it could change the plane and where it is quite dramatically. Okay, the second one is extrapolation, which we've seen a little bit with quiz. The third quiz we just had, where does it make sense to, remember we talked about how you need to predict within your data, not outside your data, because I think we were predicting a toddler's height of being, or an age or something like that. It was outside the bounds, that's for sure. Can't remember offhand. You should be able to access that quiz on Gradescope and see how you did, where you went wrong, and that. But that is called extrapolation. So for predictive, this is predictive analytics. So for predictive purposes, we want to forecast you want to interpolate within our data. Don't go out. It's risky because you could have an error. So if you look at, well, our data set, let's say age, let's say the highest age was 45, then you wouldn't want to get a prediction for an 80-year-old. It's just, there was no data between 45 and 80, and it would just be risky using that. Okay, so it has to be within the ages that you collected and the time spent on the chat feature. If you go outside that, it's called extrapolation. What you want to do is interpolation, stay within side. Okay. So don't go outside the range. Nonlinearity, be careful. You want to make sure that it is a linear, these relationships are linear. Okay. If they're not, then you need to use nonlinear regression methods. Okay, which we don't cover in this course, but they do exist, and that's what you would do. So just remember, everything that we've done in chapter 14 and 15 assumes that the relationships are all linear. Okay. All right. Collinearity, that's when two or more of the independent variables are highly correlated amongst themselves, which can cause issues. It can cause prediction intervals. Your model may not be a good predictive model if you have that. So like if you have height and weight as two different predictors, well, they could be really correlated, or height and shoe size predicting weight or something like that, that if they're really correlated among themselves, we call that multicollinearity. And it increases the variance of the regression coefficients, making it unstable. Small sample sizes in relation to the number of variables. So if you have 26 customers, like we did, you would not want like 10 predictors. That would just be, we call that the curse of dimensionality, because it's just too many dimensions for just a small number of customers or data points. So you want to be careful with that. And the less predictors you have, the better, right? We always say that it's the more simple model. It's not the complex model that's better. It's the more simple model that is usually best. If the sample size is not substantially larger than the number of predictor variables or the variables in the model, then you might get a large R squared value even when there's no relationship. So you might go, hey, I have a really good model, but the relationships, that may be artificial. Okay. And you want to be able to identify which is the dependent variable. The dependent variable is our Y, right? And our independent variables are our X1, X2, X3 to XK, right? The independent variables. All right. Dummy. We call them dummy because they are categorical variables such as yes, no, right? So yes, no. So like if I was going to use whether a customer has a license or not, right? A driver's license or not, the answer is yes, no. There's no numbers. So we assign numbers to them. That's why they're called dummy variables, because we're just giving them numbers. So we're giving no a 0, and most of the time we give yes a 1. Okay. And they are used to tell the difference between the slopes. The lines are usually parallel, and the only change is the intercept. That's the only thing that's different. But we can find out in the same manner whether it's statistically significant or not. So the predictions will be based on whether 0 or 1 is used. So I'll show you how it's used. So we sometimes have salary anomaly studies where we want to see if males are being paid higher than females or vice versa. Here, the males are 0 and the females are 1. And it really doesn't matter who you give 0 and who you give 1. We could have easily have given the males 1 and the females 0. Like, it just doesn't matter. You just have to give one 0 and be consistent, and the other one 1. And then you can look at monthly salary, for example, and the age is every decade. The age is in decades. So 3.2 would be 32 years. Monthly salary is in thousands, so that would be 15,480 gross salary. And then we have the gender 0. In this case, they've been defined as male 0 and female. Small set. How many did I use here? 15 employees. This was a bank, leave. And then we have here, we also look at the summary statistics. You all know how to do that. You can get for the males, you can go, well, what's the average monthly salary? And it's 1578.625 and 1,578. Yeah, I think I had said 15,000 monthly salary. That would be really high. It's 1,578 versus the females 1,091. And right away, the red flags go up and go, wait a minute. Should we look at, the ages or the number of years of experience, or should we look at, what their education is? Those are usually big drivers for predicting monthly salary or predicting salary. And the average age for the males are older. So, but we want to formally test and see if we have gender discrimination. And you can do that by seeing if gender is statistically significant or not. Or is it related to the salary? If it is, then we have discrimination, gender discrimination. If it isn't, If it's not significant, then we don't have. So let's take a look at this. Here's the output from Excel. We have our coefficients. Age is X1 and gender. And this and Y, just remember Y was salary, or what was it? Monthly salary? Monthly salary. It doesn't come out in the output because it's just the Y, right? Y is monthly salary. And it would be a Y hat. And so what is the multiple regression equation? Well, it's going to be monthly salary. And you can put a big hat on that, or you can write it in notation, is equal to 1.190744677. And I wasn't kidding when I said carry many decimals. This is what Excel will do. Plus, we're going to add 0.111220164 times age plus, oh, it's not plus, it's subtract 0.4586, 4586, 8406 times gender. And that is if gender is 1, then we keep that value. If gender is 0, that's male, then that value goes to 0. Okay, so you end up with 2 lines. So this is going to be, I'm just going to write it out here. That would be B1 plus B1 X1 plus B2 X2. Just know that this is your B0, your B1, and your B2, right? That's the notation. Monthly salary. And you can fill in what the B's are. I'm just kind of speeding it up a little. And what is the regression equation for males? So for males, we would put in gender equals 0, I believe it was, right? So it would be Y hat equals 1.190744677 plus 0.111220164 times X1, which is age, subtract, and it's 0. So it's just going to be 0.45868406 times 0. So that's gone. So it's just going to boil down to this. That's the equation for the males. And the equation for the females is going to be 1.190744677 plus 0.111220164, subtract 0.45868406 times 1. I multiply it, but that's why they're called dummy variables. It's binary. They're called a binary variable, zeros and ones. And so we have a 0 and 1. Then that can be simplified. If I go 1.190744677 and I subtract this, I'm going to get a different intercept. And that's the only difference between the male equation and the female equation is the intercept is different. So we end up with, we just subtract that. We end up with, let me just find my notes. I didn't carry as many decimals in my notes. Does anybody have the new intercept? 44677 subtract 0.4586 8406. It's saying syntax error. What am I doing? 19. Does anybody have 0.45868406? I got 0.7320 60617 plus, we're definitely acting like computers here with all these numbers. This should have an X1. That should have an X1 in there. There we have it. So that's the equation for the females right here. The equation for the males and the equation for the females. The only difference is the intercept is different. So if we were to draw this picture, let's see what it looks like right here. That's what it looks like. Females and the males. I have swapped the intercept, but the blue line is going to be 1.19. That's going to be the males. And you can see they're parallel, and they should be. But now we're going to see for significance and to see if we have gender discrimination or not. If they're close, then there's not much difference. But if that distance between them is significant in a scientific manner, then we have discrimination. So let's see how it's done. We have our output. Is age significantly related? So we're going to first look at age. So we want to just, we have a choice. We can use a t-test or we can use a confidence interval. Which would you like? What should we do? T-test. Yeah, let's try the t-test. So the t-test is just going to be t equals, for age, it's going to be B1 divided by S1, which is going to be 111220164. It's a bit of an overkill with this many decimals. I don't think the lab has this many decimals all over the place, but. And proofread it all. That's going to give us our t. And 20164 divided by 0.07208344. 1.543. Let's stop there. Whew, it's a lot of decimals. So let's look at the t critical value. Now, how many degrees of freedom would we have here? Well, we need the degrees of freedom. N minus K minus 1. I think N, did I say there was 15 employees? So that's going to be 15. And what is K? What is K? Yep, 2, 2, and 1. So that's going to be 15, 14, 13, 12, right? 12 degrees of freedom. Let's take a look at our F table for 12 degrees of freedom. Right here, 2.179. 2.179. Is it significant? So T is not greater than T crit, right? So therefore we cannot reject H naught, and age is out. Doesn't matter how old you are. We would want to collect more data. We would want their experience, their education, time at the company and all that, right? So that's, but in this case right now, age, we cannot reject that B1 equals 0. And so therefore age is not significantly related to salary. So we don't have any ageism happening. Although age could be significant in the sense that the older would be the senior staff and they're longer and should have that seniority pay, right? So, but at least with this data, we're not seeing it. So age, we wouldn't really say ageism. You'd have to look at the data really close to see. The senior staff has more seniority pay, right? But then it's actually, this isn't just salary though. This is starting salary. So should someone who starts at age 60 get the same starting salary as someone who's 30? Depends, you'd need more like education and experience. That's where all that comes in, right? So anyways, it's out. It's our first one. We haven't seen many variables that we could not reject. And then let's see about gender. So it's going to be T. You're going to have B2 over S2, which is going to be negative 4, 5, 8, 6, 8, 6, 8, 4, 0, 6. Divide by its standard error. 0, 5, 3, 4, 5, 8, 4, 9, 8. All right, what do we get with all those decimals? And it will be the same t-value as the previous test. Divided by 0.053. Do you get this? Does anybody? Yes, I see lots of agreement. And what was our test statistic or the critical? 2.179. T crit is 2.179. So in this case, since, so we have here, since the T test is greater than, quite a bit, than the T critical value, we reject, right? We reject the H naught, that B2 equals 0, and accept that the opposite, which is B2, does not equal 0. And so therefore we conclude that gender is significantly related to starting salary. Gender discrimination? Yes, we found it. And so this is what they do. A lot of universities have been doing this with the male and females. I don't know if you've seen it in the news, Waterloo and Toronto and everywhere. And this is a similar test what they would do. And if they find that you reject the null hypothesis and gender is significant, it means that it's related and there is at play a significant difference. The difference is statistically significant. Yeah. 0.053. Yeah, it's coming from this value here. I will highlight the values that I used. That was the numerator, and that is the denominator. Okay, so that's how they do it. It's one way they do it. They also analyze the numerics like we did here. They look at that. They also slice and dice and try and stratify the data to see the seniority pay versus this. Yeah, sure. 25? Mm-hmm. Yeah, so those are our two lines, and they are parallel, and it turns out the distance between them is significant, which now if they're closer together, that means that men and women are paid similarly with this data set at this location, but the distance between the two parallel lines is significant, meaning they're not being paid the same. Okay, so if we look at this picture, can I move it now? Are you good? Yeah, you can see here that we've shown with the t-test that there is a significant difference between the two equations. So those are called dummy variables. We also call them indicator variables, where we have like an indicator. We use a capital I for indicator, where we go 0 is no and 1 is yes, sort of like that. We do some sort of thing like that. And so we know that it's going to be a 1 or a 0. It's a binary variable, right? I have another example using, yes. So if you have real estate, right? Real estate can use these methods to be able to get a fair market value of someone's home. And we know that in certain cities, like London, if you have a pool, it can actually raise the costs of your home. It can be worth more. If it's on a corner lot, it can be worth more. If it's near a Costco, it can be worth more. If it's near a dump, it can be worth less. So it depends on location, and it depends on the size of the home, how many bathrooms, how many bedrooms, and so forth. But if it's a city like, say, Northern Ontario, where there's a lake, the pools actually decrease the house price, because a lot of people up there have lakes and they don't really want the pool, and they don't want the pool, they have the lake. So this here is data showing 80 homes. So this goes on and on and on. I've cut it off from the Excel sheet. It would keep going if I cut and paste more. And so the dummy variable in this case is the binary variable pool. Does the house have a pool? Yes, which is 1. No, 0. So you can see it just has these 1s and 0s, right? But you can see the niceness rating is continuous, right? The higher the number, the better the rating. The number of bathrooms, it's continuous. Is it 2.5 or 2 bathrooms or 3.5 half bathrooms and full bathrooms? And then here's the square feet, and then corresponding to the price. So we can use this to build a multiple regression model with the dummy variable pool. How many, we would have Y, this would be X1, this would be X2, this would be X3, this would be X4. We have 4 predictors. We could have more too, but you have to be careful. We only have 80 homes, so all right. So we can then use it so that a realtor would use this, or even just even an economist would use this to know what's the average price of home in a city, or right, for economic purposes. So you could then get the output. So this is the raw data, some of it, because there's 80 homes, there's many more. And then here's the output showing the Excel coefficients and standard errors. We have the size, bathrooms, rating, and pool. So the coefficients, just know this would be B0, B1, B2, B3, B4. This is X1, X2, X3, X4, and this would be S0, S1, S2, S3, S4. Just know what is the output showing us. So what is the multiple regression equation? And you could just call it price in thousands. Lots of, I might just round. I'm going to probably round these, just why not? Just to get it all in here. So the first one is going to be 24.976 plus, it's going to be 0.053 times bathrooms plus 10.043 times, oh, that's size. That should be size, right? Jump in if you see me write something strange. This will be the size of the home. And then this will be plus the bathrooms. 10.043 times the bathrooms I'll just say bath, plus 10.042 times the ratings. And then plus, here's our dummy variable, 0.862 times the pool. And the pool will have only two numbers that can be entered in there, 0, no pool, 1, yes pool. So what is the regression equation for homes with a pool? And then we can put that in. So let's see, we could keep it as price. I'm just going to go here, price equals with a pool. So that's going to be a 1. So we're going to do, what you want to do is, you know that pool is going to be 1. I'm going to add those two together. So I'm going to take 24.97603818, and I'm going to add it to 25.86232229. That's going to be the intercept. 50.838. That's the new intercept with the pool. Everything else stays constant. And that's it. Without a pool, the price of the homes is just simply going to be the same constant, 976. Everything else is going to stay the same, but it's going to get rid of, the pool will be gone completely. And the intercept stays the same. So with a pool, the intercept changes. And so you can see, it really has an effect, right? You're going to have, there's really going to be a real big distance. I should have plotted these to see it, but we can go through each one now and see which one is significant or not. Okay, so we need to get 4 t-tests and just compare it to 1 critical value. So let's do that. So which of the regression equations, or which one of the regressors are significant? And we'll do that. I'm going to grab this. Everyone have this so far? We're good? So we're going to grab this. So we're going to do, let's do size first. So that's going to be B1 over S1. We're going to do B2 over S2. We're going to do 3 is going to be B3 over S3. And the final one will be B4, T4, B4 over S4. And we need to get all those values. If you can help me get those, that would be good. I need to plug in because I'm losing power, but if you can help me get those values, you just literally take the coefficient, divide it by its corresponding standard error, and we're going to compare it to 1 critical value, and we'll know exactly if the value is significant in predicting the house price or not. And of course, we would have plotted all these relationships, get the plots, what they look like. And maybe I'll do that for next time. And also what the equations look like with and without a pool. Does it make a difference for this city? It depends on the city, like I said, whether it's significant or not to have a pool. In London, I think it is, because London doesn't really have a lake right beside it. You have to drive. There's a lot of pools in London too. So it depends on location. I'm going to put this in for, so we need to just add these in. So right? I'm just going to do that. If you guys can help me get those, we'll just round them to 3 decibels. That's all we need. The next one. Seven, 9, 1, 4, 9, 3, 9. Yep. And then finally 25.8623229 divided by 3.57471224. All right. Do we have any T's? We also want to get the critical value. The T critical value, degrees of freedom for this here will be n minus k minus 1, which was 80 ohms. Subtract, what's k? 4, good. N minus 1, 75? 75. So I'm going to try and get that critical value. Well, let's get these T's. Let's grab the T's. So 5, 6, 3, 5, 7, 2, 2. What have you got? Perfect. That's what I get too. 7.982. Verified. All right. And the next one. 0007. Anybody have the second T? Second T? The second T? Yep. 693? I get 2.652, but we can do, I'll do it one more time. Yep. It's close. It's quite possible I entered something in. 252, 3.72871. No, you're right. I was wrong. 2.693. Perfect. Okay. Number 3, let me do this so I can verify. Zero, 4, 2, 0, 3, 1, 9, 7. Anybody have a third number, third T? We're looking, yep. Yes, good, 12.687. And finally, the last one, I'm going to just enter 25.86. What's it? 4, 7, 1, 2, 1, 2, 4. Anybody got the last one? Yes, at the back? 7.2347. Yes, good. So I'm just going to make this a little neater. 7. So everyone can see this. 7.235. I'm going to just stop there. That's good, but you have more precision. That's good. Our critical value, we just need one critical T value here. Let's get that. It's going to be 75 degrees of freedom. So we'll take 70, Remember, way back, we said it's always best to err on the side of caution, to always go down on these, go down to the lower one. Instead of, we could have used 80, but 70 is probably better. And stay there, we'll do 1.994. Okay, this is looking interesting because 1.994 is our critical value. I would say they are all in, right? They're all greater than 1.994, right? So this one's in, this one's statistical significant, all of them, all four. Right, they're all significantly related to price. So